webinar of the Infrared Science Interest Group, or it's actually now the Infrared Science and Technology Interest Group, STIG. My name is Volker Tolz. I will be moderating the webinar today, and I'm an astronomer at the Harvard-Smithsonian Center for Astrophysics, and I'm a member of the STIG Leadership Council. Before I introduce our speaker, I will provide some brief instructions for how the webinar will work. So first, please submit all your questions via the chat window. And you can find these instructions in the chat window as well. Please submit your questions as they come up instead of waiting until the end of the talk. During the question answer period at the end of the talk, you can also use the raise hand feature. The moderator or me will unmute participants who have their hands raised to allow them to ask their questions directly to the speaker. Please submit any additional feedback, comments, questions for the Leadership Council through the chat window as well. We will answer these questions at the end of the hour or send an email response afterwards if we run out of time during the webinar. Please also report any technical difficulties in the chat window so we can try to address them. This webinar will be recorded. You already heard that the recording has started, and it will be made available at a later time on the STIG webpage, and you can find the link to the webpage at the end of the instructions. So now I would like to introduce our speaker for today, Dr. Patrick Breysse. He received his PhD from Johns Hopkins. His advisor was Mark Kamionkowski. From Johns Hopkins, he moved on to a postdoctoral fellowship at NYU Center for Cosmology and Particle Physics, where he studied cosmology and galaxy evolution. In between, he stopped for a postdoctoral fellowship at the Canadian Institute for Theoretical Astrophysics for his work primarily focused on exciting new line intensity mapping surveys, which provide a new window into subjects ranging from the large-scale structure of the universe to the interstellar media of high redshift galaxies. He spends most of his time modeling signals for upcoming intensity mapping experiments, developing new analysis techniques to extract useful physics from them, and analyzing and interpreting the data as it becomes available. He is a collaborator of the Carbon Monoxide Mapping Array Pathfinder COMAP, the Cerro Atacama Telescope Prime, CCAT-P, and the Experiment for Cryogenic Large Aperture Intensity Mapping, XCLAIM. So Patrick, please take it away.
All right, thank you, Volker, for the introduction. And thank you for the invitation to come speak on this webinar. Just want to do a quick check that everyone can hear me and see my slides before I get into things.
I can hear you speaking for the other people, so.
All right, great. Okay, so as Volker said, I spend most of my time thinking about this exciting new class of astronomical observations called line intensity mapping. I'm a member of several different collaborations, as you mentioned. Today, I'm going to talk about the results from one of those projects, the Carbon Monoxide Mapping Array Project, or COMAP. Because I'm a cosmologist by training, I am obligated by law to open with this image, this kind of schematic view of the history of the universe from the Big Bang to the present day, which I'm sure most of us have seen many a time. And over the last few decades, our collective understanding of the history that is illustrated in this picture has improved dramatically through two primary sources of data. The first is the cosmic microwave background, effectively a two-dimensional map of, after a bunch of approximations, the density of the universe at a single surface at a redshift of about 1100 when the universe was quite young. And the second data set is ever more sophisticated large galaxy surveys in the relatively more local universe by measuring the positions in redshift of thousands and upon thousands of galaxies now. We can build up a very detailed picture of the three-dimensional structure of the universe. And by studying the structure in these maps, we can learn about the overall growth of structure in the universe, things like dark matter and dark energy. And by looking at the luminosities of the galaxies themselves, we can learn about how the galaxies formed and evolved to get to the present day. And so all of this has led to what has been called the era of precision cosmology, this incredible increase in our understanding of the history of the universe, unprecedented precision in all kinds of measurements. But there's a kind of fundamental problem with this whole picture, and that is that these galaxy surveys, the CMB gives you a two-dimensional image at very high redshift. Galaxy surveys themselves become harder and harder to do as you extend out to higher and higher redshift, due to the very basic astronomical fact that faraway objects are harder to see. So that leaves something of a gap in our observations of the history of the universe, a period where we don't have the same kind of exquisite detail and precision that we have either in the distant universe or in the very local universe. And this can be a fairly large gap, depending on how you count it. This is a plot of the co-moving volume of the universe available out to a given redshift. So if we observe the entire universe out to redshift 1, say, that would only cover about 1% of the total volume of the universe. Even going out to redshift of a few only gets you out to 10% or so. There's potentially quite a lot of universe, of volume, that is we're just not able to measure in this kind of detail because it's so expensive to detect individual objects. And there's a lot of exciting, interesting things that happen during this time. This is the period when the first stars were born. We call it so-called cosmic dawn, when the light from those first stars ionized the intergalactic medium for the first time, the period we call reionization, which can be thought of as the last great phase transition that the universe went through. During this period, galaxies formed and evolved and grew and merged, and supermassive black holes formed and had some poorly understood effect on the growth of those galaxies. And towards the tail end of this less well-probed region, we reach the peak of cosmic star formation at about redshift 2, before the total amount of star formation in the universe declines down to the present day. And it's just difficult to measure these things in the kind of detail we're used to in the more local universe, again, because we can't go find thousands upon thousands of galaxies nearly as easily. So in this talk, I'm going to focus on 2 of these periods of cosmic history, the epoch of reionization and the epoch of galaxy assembly. And I'm going to talk about how the COMAP experiment has begun shedding light on these relatively unexplored periods of cosmic history, and how it's going to shed much more light going forward as the experiment progresses. So COMAP is, as I said at the beginning, what we call a line intensity mapping experiment. So line intensity mapping is a tool to get around this fundamental difficulty of observing individual objects. And the way I like to summarize it is to say that intensity mapping is a technique that uses all of the photons hitting your telescope to learn about the distant universe. So what do I mean by that? Well, let's say I take a kind of cartoon image of a galaxy spectroscopic survey. Here, this kind of toy simulation I've plotted here, every dot in this image is the location of a galaxy. This is a simulated few square degree field. And I've assigned each galaxy a CO luminosity based on some model. I've picked CO because COMAP is a CO experiment, and we'll talk more about that later. So if I wanted to map this, like a blind map of this field with, say, VLA, I could spend 4,500 hours, which is a quite substantial VLA campaign, and I would detect all of the galaxies I've marked in red. That corresponds to about 1% of all of the sources in this volume. Now, 1% is not a lot. The fact that you can't see very many sources, there's Poisson limits on the precision of any kind of cosmological or astrophysical measurement you want to do with those. But also, if I'm detecting the 99th percentile of luminous galaxies, those galaxies are probably unusual in some way. They're probably not representative of the whole population, of what the state of galaxy evolution is. at this simulation, which happens to be taking place at a redshift of about 3. However, all of these fainter galaxies marked in gray are still emitting photons. Those photons are still streaming through space and hitting our detector and being recorded. We're just not using the information from those photons because we can't say that any of these pixels is bright enough above our noise threshold to definitively have a galaxy in that spot. So the idea of intensity mapping at a base level is to use those extra photons. And so we do that by saying, if we're interested in the statistical properties of the whole galaxy population, we don't actually care necessarily about observing any individual object. So we can make a map with relatively coarse resolution that picks up the aggregate emission from all of the sources in a beam, rather than trying to identify individual objects. And that produces something like this cartoon on the right, where this is the luminosity now, the smoothed over luminosity of the CO line coming from all of these galaxies. You can see that the blotches on the right-hand panel follow the similar large-scale structure as the galaxies on the left, because they are, of course, coming from those galaxies. But you can also see areas like the lower left of both of these plots, where there's no single bright individually detected galaxy, but I still pick up the fluctuations from those fainter objects in the intensity map. This idea of intensity mapping is I can use the statistics of these fluctuations to learn about the aggregate properties of this entire galaxy distribution. You might be familiar with this kind of unresolved background observation from things like the cosmic infrared background and other unresolved backgrounds. What sets line intensity mapping apart, of course, if you want to hear more about this basic idea, there's this archive white paper from a few years ago summarizing one of our workshops on the subject. Feel free to go check it out. Sorry for that. So if you want to learn more, if you're familiar with things like the cosmic infrared background, the idea of line intensity mapping, what sets it apart from those is that we target a single spectral line, a feature that has a very narrow frequency range. And the reason why that's useful is if we know the frequency our emission is coming from, we can tune our observing frequency to very precisely set the redshift we're observing. And more importantly, we can observe at many different closely spaced frequencies to build up a 3-dimensional tomographic map of the large-scale structure of the universe with quite good redshift precision, without, again, the difficulty of obtaining spectra on many, many individual objects. But to summarize the basic idea of intensity mapping, the galaxy surveys, your standard go identify a bunch of sources surveys, tell you a lot about the detailed properties of the very brightest galaxies in a volume. Intensity maps, on the other hand, offer a very powerful complement to that by telling you the statistical properties of the entire galaxy population. And so that tells you about what's going on in galaxies you can't see individually. If there's a lot of star formation in faint galaxies, for example, it will appear in the intensity map and not in the galaxy survey. And so this is the basic idea that we're trying to do with COMAP. Because this idea, this is a fairly simple but powerful idea, this intensity mapping concept, it has driven a lot of experimental interest over the last decade or two. So this schematic is from an Astro 2020 white paper that I co-wrote with some collaborators of mine, summarizing the alphabet soup of intensity mapping experiments. So odds are, if you've heard of this intensity mapping concept before, it's probably in the context of maps of the 21 centimeter line from neutral hydrogen, highlighted in this left-hand hub and spoke diagram. 21 centimeter was the first intensity mapping idea to really catch on. The idea is basically you get a map of the total amount of neutral gas in the universe. This is particularly exciting across a wide range of redshifts, especially at reionization, because you can watch the neutral intergalactic medium disappear as you scan through your frequencies of your experiment. So 21 centimeter has attracted the most interest. There are quite a few collaborations operating. Some of them have started to publish results. But just like in any other brand of astrophysics, different lines have different observational systematics. Different lines tell you different things about the astrophysical processes in your emitting objects. There's a lot of motivation to go after as many different lines as you can get your hands on. So the next most popular set of lines, which is what will be my primary focus today, is a pair of different carbon species, either rotational transitions of the carbon monoxide molecule or the fine structure transition of the C2 line at 158 microns. Glossing over a lot of subtleties in interstellar medium physics, both of these lines effectively act as tracers of star formation activity in the high redshift universe. And so again, if we think back to reionization, if we have 21 centimeter lines mapping the disappearance of the neutral IgM, a CO or C2 experiment would tell you about the objects that are emitting the photons that are causing that reionization. And so there's been a significant amount of interest in these lines because star formation is such an important process in understanding galaxies. And also, what I'm not going to talk about today, there's a collection of experiments, including very excitingly, NASA's SphereX mid-X satellite that's supposed to launch in the next couple of years that can do mapping of a bunch of other optical infrared UV lines. There's a lot of exciting work there that I will not have time to talk about. But as I said, my focus today is going to be on the COMAP experiment, which is one of these maps tracing, as the name suggests, carbon monoxide. So COMAP, you can get a pretty good idea of what we're doing just by looking at the acronym. So of course, as I said, we are targeting carbon monoxide molecules. CO as a asymmetric diatomic molecule has this very nice series of evenly spaced rotational transitions at the hundreds of gigahertz frequencies. CMAP in particular is going to focus on the lowest two of these transitions, the 1 to 0 line at 115 gigahertz and the 2 to 1 line at 230 gigahertz. CO as CMAP is, as I said, an intensity mapping experiment. We are trying to measure carbon monoxide using this intensity mapping technique. The instrument itself is a 19 feed focal plane array built on a 10-meter telescope at the Owens Valley Radio Observatory. The Pathfinder is a single one of these 19 feet arrays on a 10-meter dish. We have long-term plans to expand to more copies of this dish and receiver setup to build up more sensitivity. And then we have a detailed project timeline consisting of the initial Pathfinder observations, which are going to take up most of my time today, targeting the CO 1 to 0 line at about redshift 3, followed by a future expansion, which I'll talk about at the end of the talk, extending our observations out to the epoch of reionization. So as I said, CMAP is placed on this 10.4 meter telescope at the Owens Valley Radio Observatory managed by Caltech. This picture is from one of our in-person collaboration meetings back when that was a thing you could have. This receiver at the center of the dish hosts these 19 feed horns, which are coupled to 19 LNAs, which we use to measure the signal. I will plead theorist in that I will not be going into much detail about the structure of the instrument, but we do have papers on it. If you want to go look it up, I will link those papers later on as we go. COMAP is a collaboration of several North American and European universities. Kind of the core group, our PI and our main hardware team is at Caltech in the Owens Valley Radio Observatory. We have a substantial placement at the University of Oslo in Norway, handling a lot of our pipeline and data analysis. And we have collaborators from many other universities, including myself at NYU, handling things ranging from theory and modeling to an auxiliary galactic science survey, which I'll talk a little bit about later. CMAP was, the initial seed funding for CMAP came from a technology development grant from the Keck Institute for Space Studies before primary main science operations being funded by the National Science Foundation. So why we want to go after CO in particular? Well, as I mentioned previously, carbon monoxide molecules by definition form in cold molecular gas clouds, which is the same environment, which is the primary fuel for star formation. So that means that modulo any number of details, because interstellar medium physics is complicated, CO is a very good tracer of star formation activity in high redshift galaxies. And star formation is key to understanding the evolution of those galaxies. So it gives very useful insights into how galaxies grow and evolve. And as I mentioned previously, at reionization specifically, it traces the sources of the ionizing photons by, again, being correlated with star formation rate. CO is also observationally very convenient. The ladder of equally spaced transitions I mentioned enables a lot of easy cross correlations, which, especially as we push out to reionization, will be very important for removing systematics and verifying that we've actually measured a high redshift signal. Also, critically for an intensity mapping line, CO has very low foregrounds. Again, if you're familiar with 21 centimeter intensity mapping, things like Hera and CHIME, the foregrounds from the Milky Way galactic synchrotron in those experiments can easily be 3 to 5 orders of magnitude brighter than the signal, making it very difficult to isolate the very faint cosmological signal against such strong contamination. Other lines like C2 suffer from a problem where other spurious emission lines at different redshifts are redshifted into the same observational frequency band. So I'm not just measuring, say, C2 at redshift 6, I also have to deal with various higher order CO rotational lines that I have to try and separate out somehow. CO 1 to 0, on the other hand, is expected to be the brightest line at our frequency range. We don't expect to have to deal with line contamination. And at 30 gigahertz, the continuum foreground issues are much lower and are much more easy to remove and control, to the point where they're honestly not our primary concern at all, to the degree they are in 21 centimeter. So that is a really nice argument for trying to do these CO experiments early on. So as I said, COMAP, the kind of seed was planted at this first billion years workshop hosted by the Keck Institute just over 10 years ago now. Pathfinder construction began in 2015 under funding from the National Science Foundation, and our Pathfinder observing campaign began in the summer of 2019. So we've been observing for going on 3 years now. The majority of my talk will be taken up by results from our first year of observations, which we have finished. We recently finished analyzing and published papers on. So when I say we're targeting the first results from the COMAP Pathfinder, I'm talking about results from this first season of data, this first, I think it's officially 13 months of data that we have finished interpreting. Last November, we put on archive these 7 early science papers led by all of these people pictured here. I am pleased to announce that as of last Friday, all of these papers have been accepted to the Astrophysical Journal, and so they will be appearing in press shortly. I'll put archive links to these papers at the end of the talk, so they appear in the recording. So obviously, there's a ton of information in these papers that I will not begin to have time to get into all of today. So I encourage anyone who's interested to, particularly this overview paper provides a very nice summary of the other papers if you are interested in reading more. We also have an 8th paper in preparation led by Delaney Dunn, a graduate student at Caltech, looking at cross-correlating our early science maps with the BOSS spectroscopic galaxy survey that we hope to come out in the next few months, just to advertise the great work Delaney's doing. So our first season, our Pathfinder data consists of maps of 3 fields, each of which are about 4 square degrees. These fields in white are shown on a background of the Planck 30 gigahertz broadband data. The field selection was chosen, 1, to avoid bright radio point sources that might contaminate our data, but they were also chosen for overlap with the Hobby-Eberle Telescope Dark Energy Experiment, which is an IFU spectroscopic survey of Lyman alpha emitters covering our same redshift range. The idea, as I'll talk more about in a little bit, is that this provides a spectroscopic galaxy data set of our redshift range that we can use for cross correlations, which both opens up new science possibilities beyond which either could do individually, but also offers the opportunity to confirm solidly that we are in fact observing high redshift galaxies, not some previously unknown foreground contamination. The first season data takes the form of, we scan over these fields continuously. We have 2 scan patterns. We alternated in the first season between a Lissajous scan pattern shown azimuth elevation here and constant elevation scans shown in this lower panel. And in the bottom right panel, you can see some examples of the raw data coming off the telescope, the raw power picked up by the receivers. So for example, in the constant elevation scans, you can see how the power jumps every time we change elevations due to the changing atmosphere contamination. We have paper 3 in our series describes a very robust data analysis and cleaning pipeline developed by our team at the University of Oslo, which I will briefly summarize here. We start with this raw data coming off the telescope. This example is from one of the Lissajous scans. First, we apply a low pass filter to the data. So this is a I should say this is data from a single scan. So this data covers, a few hundred seconds of time. So we don't expect there to be any astrophysical signal in this data, because after all, we observed for a whole year. So the idea of this is to reduce the data coming off the telescope to something consistent with white noise. So first we apply a low pass filter to the data because we're scanning back and forth this quickly. Any long-term variation is not going to be astrophysical. It's going to be, for example, atmospheric. And we subtract off. So we subtract off these kind of long time variations. And then we know the elevation pattern of our telescope, so we can subtract off a template of what we expect the atmosphere depth to be as we scan back and forth, which in the Lissajous case gets rid of this oscillatory pattern in the data. Our next step is to subtract out a low polynomial that effectively removes any part of our data that is correlated in frequency. This is because, in the astrophysical signal, the frequency direction corresponds to the redshift direction. So we expect the signal to the astrophysical signal to be quite different in every frequency channel. Whereas things like the atmosphere or astrophysical foregrounds, continuum foregrounds like dust or the cosmic infrared background, those are smooth in frequency space. So by removing things that are correlated in frequency, we remove things like astrophysical foregrounds that might be contaminating our data. If you are familiar with 21 centimeter intensity mapping, this is our equivalent of removing the wedge from our data. If you're not familiar with 21 centimeter, don't worry about that term. It's not important for understanding the rest of my talk. And finally, again, we have 19 feeds, each seeing a slightly different part of the sky. So we use a principal component analysis to subtract out any remaining signals that are correlated between all of those feeds, because they should be each seeing slightly different astrophysical signal. So anything correlated between the feeds is not something we want in our final data. So if you look at the Fourier transform, the time-space Fourier transform of these data plots, you get something like this plot here, where the different colors going from top to bottom represent each of these subtraction steps. The goal is to produce data consistent with white noise, which corresponds to a flat line on this plot. Before any subtraction, we have this steeply rising 1/f noise feature, which corresponds to a lot of correlated noise in our time order data. And we have this big peak corresponding to the frequency of our scan. But you can see as we apply each of these steps, this 1/f noise is reduced until we're left with our final data, which is consistent with white noise. So after applying all of this, we can take our cleaned time order data, combine it with the pointing information from our telescope, and we can create our actual intensity maps. Now, for our first season, we only have 20% of our planned observing time. We don't really expect there to be any signal at this noise level. So our goal here is to produce maps that are consistent with white noise. If we can do that, that means that we have successfully controlled our systematics down to our current level of sensitivity, which for a Pathfinder experiment doing this new type of observation is a not straightforward and very difficult goal. And so these maps, though, if you look at them by eye, these look like white noise to me, but we can also apply various statistical tests to show that these maps are in fact consistent with white noise at the level we expect at our current level of sensitivity. Each one of these shows a map of one of our fields. Like I said, each corresponds to about 4 square degrees. Each one of them is a single frequency channel of the map. So for each one of these, you should think of it as part of a stack of about 250 similar images corresponding to a fractional redshift difference of about 0.004. And so this data cube is our intensity map. This is our tomographic 3-dimensional measurement of the CO emission at redshift 3. Of course, if we want to get any useful astrophysical information out of these maps, we have to reduce it to a form we can interpret. And if you give any cosmologist a new observable, the very first thing they will do is compute its power spectrum. For those, unlike me, who don't spend all their time listening to cosmology talks, power spectrum is very simple. We just take these data cubes, we Fourier transform them, and then we look at the variance of those fluctuations in Fourier space as a function of spatial scale. And so this tells you about the structures in your map on different scales, which tells you about the large scale structure of the galaxies in your volume. So intensity mapping power spectra take a generic form that looks something like this. as a function of spatial scale. The large scales, this is the wave number, so small k corresponds to large scales. The large scales are dominated by the large scale structure of the universe. Galaxies ultimately trace the dark matter in the universe. And so we have a component on large scales where the galaxies follow the power spectrum of the dark matter. If you look closely and you're familiar with these power spectra, you might be able to just make out the baryon acoustic oscillations in this model power spectrum. On small scales, because we're not actually observing a continuous density field, we're observing a smoothed over population of discrete, effectively point sources at our resolution. There is this scale independent, this flat shot noise power spectrum that appears in our data. And this is essentially due to the Poisson statistics of our galaxies. So the amplitude of this large scale term, because we've taken every galaxy and weighted it by how bright it is in CO, scales as the mean luminosity of our emitting galaxies, whereas this tells us the mean luminosity of our emitting galaxies, modulo a bias factor. And then the small scale shot noise, despite the fact that we call it noise, is actually an important part of our signal because the amplitude of this shot noise component tells us the mean square luminosity of our CO emitting galaxies. So in principle, a measurement of this entire power spectrum gives you a measurement of the first two moments of your luminosity function. And again, because we're working in this intensity mapping regime, those moments are taken over the entire distribution of galaxies, not just those that are bright enough to detect individually. This gray shaded region highlights the region where COMAP is primarily sensitive. So COMAP is primarily sensitive of scales of about a few times 10 to the minus 1 inverse megaparsecs, making us primarily sensitive to this large scale clustering information. There are complementary intensity mapping surveys that I'll briefly mention later that work in this shot noise regime at a similar redshift, giving us at the end of the day a very nice coverage of this whole range of spatial scales. Of course, this is a theorist's diagram of what the power spectrum looks like. When we make a measurement, Fourier transform these maps and apply some more sophisticated versions of take the variance as a function of spatial scales described in our power spectrum paper, we get power spectra that look like this, where the blue, orange, and green points are the individual power spectra from these three different fields. And the black points are the total power spectrum we get from the combination of all of them. So as I said, after a year of data, we don't really expect there to be any signal in this map. So our main goal is to control our systematics to the point where this power spectrum is consistent with white noise. And you can look at this by eye and see that these black points look vaguely consistent with white noise. In the papers, we have some more detailed jackknife tests and things to show that we do believe that we have successfully controlled our systematics and produced power spectra consistent with white noise. The power spectrum plotted in these units is not particularly informative without something to compare it to. So what we can do is we can take these black points and convert them into an upper limit on the total amount of power in our map. And this gives us this plot shown here. There's a lot going on in this plot, but I'll take a minute to go through individually. The first point to point out is this yellow point with error bars over here. This is, as I mentioned, another intensity mapping experiment called COPS, which is observing on smaller scales than COMAP and is primarily sensitive to that shot noise part of the power spectrum. So this is the power spectrum measurement from COPS, which is about 2.5 sigma marginal detection of power at a very similar redshift range to us. The power spectrum here, I should say, is plotted as K-P of K, not just P of K as I was showing before, to kind of compress the dynamic range of our y-axis a bit. That's why the shot noise parts of these spectra are not flat in these units. The green lines here are effectively the limits on the maximum likelihood shot noise power measured by this COPS survey and the upper limit allowed by COPS on that clustering, on that large scale clustering component. So effectively, you could think of these green points on COMAP scales as a limit on the amount of power allowed by previous measurements. This pink bar is the 95% upper limit from our first year of COMAP data that I have been showing you the maps of in previous slides. This is integrated over all of the scales we're sensitive to. And you can see that we have improved on the bounds allowed by COPS by about an order of magnitude. So this is the best measurement yet on these scales, even though we only have 20% of our data in here. All of the other lines on this plot, all of these other power spectra, are models for the CO signal at redshift 3 from the literature. The first thing you should note about these models is that from the faintest one to the brightest one spans about 2 orders of magnitude. This is because we do not understand the star formation and interstellar medium physics in redshift 3 galaxies very well at all. It is very easy to construct models that give very different answers. And without these intensity mapping measurements, it's very hard to be sure which is correct. This purple line in particular is from our early science paper. This is our collaboration's best guess at an empirical model combining the limited data available, combining this COPS point with the cold Z survey from the Very Large Array, which is a direct galaxy survey luminosity function measurement at these redshifts. So this is kind of our conservative best guess model for where we think the power spectrum could be, but it could quite easily be quite a bit higher, be a bit lower. We really don't know. This is why we need to do the measurement. But the encouraging thing about all of these different lines is that this shaded region shows the expected sensitivity of our full 5-year Pathfinder campaign. And if you look in the legend, you can see the expected integrated signal to noise from all of these measurements. And we see, for our quote unquote conservative best guess model, we predicted total signal to noise of about 9 after 5 years of observing. And even for this most pessimistic model, we still predict a solid detection of this CO power. So we can say that we expect when the Pathfinder is complete, we will have significantly improved this uncertainty. We will have reduced this from 2 orders of magnitude to at least reasonably solid understanding of where the signal is. And given that this is about the faintest model appearing in the literature, if by the end of 5 years, we've lowered our limits down all the way to here and haven't seen anything, well, then we are in a regime where the upper limit itself is very interesting because it's well below where we expect the signal to be. So the space is uncertain, but we believe we have a good experiment for nailing that down once the Pathfinder campaign is complete. Another way to express these upper limits is we can turn this limit in power spectrum space into a limit on the clustering amplitude parameter, which, as I said, is essentially a limit on the average luminosity of CO emitting galaxies. So the top half of this plot, the x-axis here, is this clustering amplitude quantity. This first point is a 2013 truly Herculean effort by Anthony Pullen to extract a measurement of this quantity by cross-correlating WMAP data with SDSS quasars. It's a Herculean effort because WMAP lacking the spectral resolution of a true intensity mapping experiment makes it very difficult to isolate CO from any other signals. These green and orange points are based on this COPS measurement. The orange point is the autocorrelation. This is effectively these green triangles. And the green point is a cross correlation with Goods North spectroscopic galaxies, which was able to improve on their limits a little bit. And then this red point is what we get when we convert this pink upper limit into this space. And we can see we have improved substantially on the limits from these other data by dint of observing at a more clustering scale. Down here, we can see our projections. This bottommost one I'll start with is what we expect to get with this full 5-year clustering, this full 5-year sensitivity on its own. This is our 9 sigma detection of this purple line. And you can see, we expect a marginal detection of that with only 3 years of data. These other 2 points, though, are what we get if we cross-correlate our COMAP data with the HETDEX spectroscopic catalog I mentioned earlier. So by doing a cross-correlation, we improve our significance dramatically to the point where we could get a potentially quite solid detection after only 3 years and improving our significance even more after 5 years. And this is all while removing a lot of potential systematics risk going forward. So at the end of the day, the CO power spectrum is nice, but we want to convert this into kind of more generally interesting astrophysical quantities. That is a very complicated process that is worthy of several talks in its own right. But for the purposes of here, since we only have an upper limit, I will focus on the simplest thing one can do with the CO survey. If I have a measurement of the average CO luminosity, that's actually the total amount of CO luminosity in the universe, I can convert that straightforwardly, at least as straightforwardly as any interstellar medium physics goes, into a measurement of the total amount of molecular gas in the universe. So this plot is showing the gray points are molecular gas measurements from direct imaging surveys. And these red points are these red boxes are existing kind of marginal significance intensity mapping detections, like that COPS point that I was showing in the previous plot. The black lines are two models from our literature models that kind of are vaguely consistent with the intensity mapping data and the galaxy survey data. This top green point, this is the upper limit we get by converting this pink power spectrum upper limit into molecular gas space. And so we can see that again, even with only a year of our data, we are still within a factor of a couple of the best existing measurements in this intensity mapping regime. After 5 years, depending on which of these models we believe to be true, we will either have a quite strong detection of this relatively bright signal predicted by these intensity mapping measurements, or we will have a measurement of this fainter model, which you can see is kind of more or less has a similar uncertainty to these galaxy survey measurements, but carries with it the confirmation that there is no significant contribution from faint galaxies, which have not been seen by these galaxy surveys, which is the unique benefit we get by observing in the intensity mapping regime. So we expect to have this very nice measurement once our full Pathfinder campaign is complete. Oh, yes, now I have them labeled. Wrapping up my discussion of the Pathfinder, I will just very briefly mention that we also have an auxiliary galactic plane survey we're doing with the COMAP instrument. I am not an expert from this. I will point you to paper 6 of our series about it, but the unique frequency and spectral coverage of COMAP enables us to do things like look for anomalous microwave emission and radio recombination lines. And they're doing a lot of exciting work with that I encourage you to check out. Other projects still to come with the Pathfinder data. As I mentioned, we have this paper by Delaney Dunn, Stacking on Boss Quasars, which can both improve our signal to noise and offers intriguing possibilities for studying quasar feedback with our data. We're exploring other analyses beyond the power spectrum, including a 1-point statistics analysis I'm particularly excited about, where we basically take our maps and make a histogram and then do some statistics on that. And as I mentioned, we are working on a memorandum of understanding with the HETDEX collaboration to allow us to do this cross-correlation with HETDEX, which will give us all sorts of benefits down the line. My last couple minutes, I want to talk about the next phase of the next planned phase of the COMAP project after the Pathfinder is complete. As I said, there's this ladder of rotational lines coming from CO molecules. We focused for now on the lowest frequency line. But by observing at 30 gigahertz, we also pick up emission from the 230 gigahertz CO2 to 1 line in that same frequency band. It's coming from much higher redshift where we expect these signals to be fainter. In the 30 gigahertz data, it should be entirely subdominant. It should not be a significant contamination to our Pathfinder goals. But since I said at the beginning, our goal is to use all of the photons, then it makes sense to try and use this information, which we are recording, to learn about the epoch of granization. So the next stage of the project, which we have termed COMAP EOR, is to add a new receiver centered about 18 gigahertz, which gives us the CO1 to 0 line at the same reionization redshifts. And then we can cross-correlate these two data sets to isolate the EOR signal and learn about what kind of star formation activity is happening at these much higher redshifts. So we've recently secured partial funding for this next stage of the project in the form of an NGVLA antenna, which we can use to build. We can use as the base for our new 18 gigahertz detector. That antenna should be available in 2026, which marks our targeted date for the beginning of this COMAP EOR survey. We plan to supplement that with 2 additional copies of the 30 gigahertz Pathfinder on existing 10-meter dishes at Owens Valley, which will give us allow us to build up more sensitivity faster to go after the fainter reionization signal. So paper 7 in our series goes into great detail on how we think this measurement will happen, how the cross-correlation will be handled, what unique opportunities and challenges show up as a result of that. But I just want to highlight kind of the big picture final results of all of that, which is if we take the same molecular gas history plot I showed before I was zooming in on the redshift regime around redshift 3, Again, gray points are existing galaxy surveys, red boxes are existing intensity maps, green point is our Pathfinder upper limit. These blue and orange boxes show what we get if we take these models, extrapolating them out to randomization and forecast what we can do with COMAP EOR. So we can see that the signal gets even more uncertain as we go out to higher and higher redshift, ranging from an extremely strong detection with this setup to a modest detection or scientifically interesting upper limit. But the COMAP EOR architecture enables us to push these measurements out to very high redshift, where these direct surveys get even more and more difficult, potentially allowing exciting new insights into randomization, which can be combined with things like 21 centimeter experiments or deep observations with things like JWST and NGBLA to build up a more holistic picture of how the universe is reionized. So I will close by throwing all of the archive numbers for our early science papers up on screen, so they appear in the recording. Feel free to check out these papers. There was a lot of hard work by a lot of people, and I think they came out really well. So I will end there, and I will happily take questions. Thank you.
Well, thank you so much, Patrick, for this wonderful presentation. And we're now moving over to the question answer period. And you, again, to repeat myself, you can submit questions via the chat, or you can raise your hand and I try to unmute you that you can ask your question directly. So please. I only have a question from my side. You show all these wonderful observations. Do you actually hog the telescope for the entire time, or do you run observing campaigns on a month, let's say for a month, and then instruments are being swapped at the telescopes?
So the 8.4 meter dish is right. 10.4 meter dish we have right now is being exclusively used by COMAP. So we are effectively observing continuously for most of that first year. After that first year, we had a gap where we took the receiver off to do some maintenance and make some upgrades, clean up some things we saw in our first data. But basically, whenever we're not doing maintenance on the system, we are scanning across the sky to build up the sensitivity we need to actually make these detections.
Okay. I'm trying to unmute.
I'm unmuted.
You are unmuted. Oh, wonderful.
Yeah. Yeah, thank you so much for the presentation. I was wondering, how do you separate, how do you remove the contamination by other possible like emission lines that are coming from other redshifts from when you are analyzing the data from CO transitions?
Yeah, so for COMAP, we primarily do that by observing at 30 gigahertz, where we don't expect there to be any other lines. Fingers crossed. We hope to, that's one of the goals of the HETEX cross correlation, is to confirm that. Since it's a spectroscopic survey, we know the redshift those are coming from, so we can do a cross correlation. The cross correlation with this new 18 gigahertz receiver, effectively the CO1 to 0 is a contamination line for the CO2 to 1. So we also will use cross correlation to separate that out. There are other techniques from things like the C2 experiments I mentioned at the beginning, where if you do have an interloper lines, there are tricks where you can look at the anisotropy of the power spectrum, how it varies along the line of sight versus the plane of the sky. There are methods for masking out lower redshift lines, but we hope to not have to, we expect to not have to deal with those on this particular measurement, and we're going to use HETEX to confirm that fact observationally.
Got it, thank you.
Okay, Jens, you have a question?
Yeah, hi, thank you for this presentation. I have a question for about a figure that you showed at the beginning of your talk. So this was the first image that you had where you showed the power spectrum.
Sorry. This power spectrum or the theory one?
No, yeah, that one. So I understand this. Sorry, I'm a Milky Way observer. I still struggle with all these things very much. I understand that this plot is instrument independent. This is just the sky signal, right?
Right. This is
Okay.
I like to call it the theorist limit. This is just what we expect to be on the sky.
Yeah. And so, but this would be different for different emission lines, I suppose.
Yes. So the general shape of this, this is making a lot of assumptions about linearity that get more complicated when you move beyond this. But this kind of general shape is more or less independent of emission lines, because it just assumes that galaxies follow dark matter, or sorry, emission follows dark matter, and galaxies are discrete. So the amplitudes of these things can move around, but the general shape is pretty consistent for basically anything other than reionization era 21 centimeter, where you're not tracking galaxies themselves.
So in terms of this clustering, what is it actually what we see here in more layman's terms? These are essentially how you see voids emerge and go away. Is that reasonable?
Yeah, so basically what you're seeing is you're basically seeing, it's kind of a statistical description of this cosmic web pattern in the galaxy. So if galaxies were purely randomly distributed on the sky, you would only have that kind of flat shot noise, just Poisson statistics power. But because the positions of galaxies follow this underlying dark matter, which is ultimately, distributed non-uniformly by inflation, fluctuations during inflation, you are left with these kind of statistical fluctuations. These correlations between galaxy positions that we we summarize in this power spectrum. So effectively, it's like counting, as a function of k, we're effectively counting the size, the number of like clusters in this map as a function of spatial scale. That's kind of one approximate way to think about it, or just to say it's how non-random is the galaxy distribution.
Okay, thank you.
Any more questions? I can add one more question, and that is, how would SphereX improve your analysis or the results? What would it add?
SphereX is potentially a lot of different things that I would love to spend more time thinking about. SphereX as a kind of spectroscopic-ish galaxy survey, I would be interested in exploring possibilities for cross-correlation with SphereX galaxies. I haven't looked at that in detail, but anytime you can add another set of spectroscopic galaxies, you can get more control over your systematics, but you also open the ability to project out different aspects of the interstellar medium with your cross-correlation. SphereX also, though, can be interpreted as an intensity mapping experiment. SphereX basically measures a kind of medium resolution infrared spectrum at every point on the sky. And so you can interpret that as an intensity map. At our redshifts, primarily as I think H alpha is expected to be the dominant line at the lower redshifts where the COMAP Pathfinder is observing, and Lyman alpha maybe at higher redshifts. And so, we're trying to understand the interstellar medium of unresolved galaxies. Having multiple lines and observations to throw into a model gives you, more ability to kind of pick apart what's going on. So there's some work I'm doing here at NYU that I didn't talk about in this talk, using this suite of semi-analytic models created by Rachel Somerville and Gergo Popping here in New York, to kind of build up these models of multiple line emissions from the same underlying galaxy physics that we can then fold results from different of these experiments, including things like SphereX, into to try and build up a picture of the high redshift interstellar medium. It's a very complicated modeling task, so more data is always better.
Well, you have plenty of time to think about it, since it's still quite a few years out that the data will become available. So anyways, and I would categorize CRX under low resolution. I mean, it's somewhere between 28 and 130, which is the highest resolution. So lines, any molecular line or atomic line will be pretty much diluted.
Yeah, I guess when I call it medium resolution in my context, I guess I'm comparing it to the, you know, people have made efforts to do intensity mapping with like WMAP and Planck. And so I guess it's better resolution than those, which means it's much more feasible as an intensity mapping experiment than some of the things.
Right.
That is fair. It is low by the standards of spectrometers.
Yeah. I mean, it's higher than R of 3 or 5, but yes. Yeah. Okay, I agree. Okay, well, thank you so far. Any more questions? Well, if not, then I thank you again, Patrick, for that great presentation. And I would like to remind everybody that we have these webinars monthly on every first Tuesday of the month at 1 p.m. EST. And even if you're interested in speaking at one of the future webinars, please contact the Leadership Council. And our next webinar will be on May 3rd, and it's by Russ Gannett. And the title is Affordable Space Telescope Constellations. Okay, then thank you again, and hopefully see you next month.
Thanks again for the invitation.
You're welcome. Bye.
Bye.
Hey, Volker, I'll stop the recording.
Yeah, okay. I was